preparing to live stream.
Got it, yeah. Mhm.
Okay, it's live with about 5-second delay. I could see only Emre and Cornelia and me in the delayed YouTube feed. I should disappear now. Okay, now I disappeared. Now you two are the only one live who are on the YouTube stream.
All right.
Others are welcome to show their video as well if they want to appear on the YouTube live stream, just to show that you're here. Otherwise, you don't appear, right? You're only seen in the Zoom meeting. If you wanted a record that you were here at the kickoff, then turn on your video. Christoph, I see you there. Okay, Christoph is there. Good. Guido, you're there also.
Yeah, good morning, Toby.
And with the short delay.
Guido from Telluride.
About a 10-second delay. Now Guido appeared also. Typical outdoor Colorado scene.
Someone had to represent.
Okay. Okay, good. So you guys are take over. I can just now I can't make you host. I have to remain host, I think, to continue streaming, right?
You can make us
Anyway,
host, I think.
who else needs to be a co-host right now? Cornelia, you need to be a co-host.
I mean, not really.
And Guido needs to be a co-host. And who else needs to be a co-host?
Shih-Chii.
Shih-Chii is gonna do it from here anyway, I think, but I can make her co-host also. Anybody else needs to be co-host who's here? I think that's it. All the topic leaders also need to be co-hosts, right? Who are going to present their topic areas after a short break. I think we'll take a short break after the first couple of things.
Yep, that's correct.
We set that up.
Toby, they don't need to. They can actually share without being co-host.
We'll take care of that when we get to it. Okay. Good.
And any 10 of them are the organizers. So 40. It's for some people, they probably will just watch the recording. In Asia.
Want to come and take over? You're going to go next anyway, so you should sit there. Oh, there's Claire Hemingway.
Yeah, I can just kind of sit over here.
I think Claire needs to be co-host also, right? You need to be co-host also. Let me make you okay. So hello, Claire and Grace.
Hi.
Hello, Grace. You're going to be presenting. I'll make you all co-hosts. Going to have a lot of hosts here. It's good for us. It's like a real workshop. NSF. Let's go down here.
And I have slides for Grace and Soo-Siang and myself.
Who is that talking right now? Claire.
Yes.
Claire. Okay. Okay. So cool. So anyway, you're going to be a co-host, so you can just share your screen when you get to it.
Okay.
But I think whoever's previously sharing a screen is just going to have to stop sharing before you can share.
No worries.
Okay, cool. All good then, I think.
Okay. So should we start? I see the list of participants. Number of participants is going up, but we'll just start with the introductions here. So hi, everybody. So my name is Emery Nefci. I am officially the host today, although you would see probably Toby as being host. That's just for technical issues for getting this video streaming on YouTube. So just so that you know, this session is recorded and also being streamed live on YouTube. So a few words about myself. So I'm one of the organizers, along with Shih-Chii, Guido, Cornelia, Andres, and a couple of more people, Terry Stewart. I'm just for myself, I'm a professor at UC Irvine, and also since very recently in RWTH Aachen in Germany and the Forschungszentrum Jülich in Germany. So today's plan is that we're going to have a short introduction to the workshop by Cornelia and Guido, who are already here. Followed by introduction to neuromorphic engineering by Shih-Chii, followed by our colleagues from NSF, who will discuss about the funding opportunities, but also the NSF activities in the area. And then after this, we'll have an introduction to the topic areas and a discussion hosted by Andreas Andreu. Okay, so I think Cornelia and Guido.
Okay, so welcome to the 2021 Telluride Neuromorphic Cognition Engineering Workshop. We're excited about the strong interest. As of today, there were 595 people registered. Many of you know the workshop has a very long tradition. We have had 26 physical workshops in Telluride, and this is our second workshop with virtual format. The workshop has been special because of its unique format. It has a tradition of bringing together senior researchers and students from a variety of fields, neuroscience, psychology, and engineering, among others, to exchange ideas. In addition to the physical workshop, we also will have this year's lectures, as well as 4 hands-on working groups. This week, we will have every day 2 to 2.5 hours of lectures covering topics such as introduction to the field, social cognition, ethic issues. We will also have an introduction to the working groups and a lecture and a panel discussions on topics related to each of the groups. The following 2 weeks, you can participate in projects organized by the working groups. In addition, there will be general lectures organized by each of them, as you can see from the schedule. Our workshop has been sponsored for many years by the NSF. In addition, we also had funding from the DoD and from companies. With the growing success of neuromorphic engineering and the emergence of neuromorphic companies, this support has been increasing. The workshop has been instrumental in growing this field. And neuromorphic engineering has come a long way. Hardware for sensing and computing has become available for research and also for applications. Future efforts can now focus on computing with this hardware and developing new theories and algorithms to work with these neuromorphic devices. Our recent funding has been an NSF grant under the program Accelerating Research through International Network-to-Network Collaborations, short AccelNet. Ours is on neuromorphic perception, action, and cognition. Through this opportunity, we will network the neuromorphic engineering communities with communities of computational neuroscientists, roboticists, control theorists. researchers working on vector symbolic architectures and computer vision. The funding will sponsor the Telluride workshop for the next years. It will fund an immersive scholarship program for students and researchers to visit other labs, for collaborative projects for a semester. We will also organize 2 competitions on neuromorphic challenges, a few scholarships for students to attend the Telluride workshop, and organizational meetings. Our sponsors, Claire Hemingway from the Office of International Science and Engineering, and Soo-Siang Lim from the Division of Behavioral and Cognitive Sciences, are here today with us. Soo-Siang has believed in this group and supported it through different programs over the years. This workshop would not have been possible without her. So Claire and Soo-Siang will now explain the program to us, after which Claire Haung will talk about new engineering opportunities. So let me pass on to Claire.
Great, thank you so much. We're really pleased to be here, and I am delighted actually to have this chance. I know that everyone's having to pivot to virtual meetings, and that's of course been a challenge for everyone, but it does provide an opportunity for those of us who otherwise wouldn't necessarily participate to get a glimpse in. So first, I just want to say thank you for being able to pivot so beautifully. It's a real pleasure to get to glimpse in. And it gives a great opportunity to acknowledge the exciting work that you're doing and the exciting work that is being led by Cornelia and colleagues. So I'm grateful for this. So I'm going to very briefly share a few slides with you. And I have here the abstract title for the award in AccelNet. And I'm just going to spend a few minutes talking about AccelNet briefly, and then provide time for my colleagues to talk as well. Bear with me if I'm a little inadept at moving slides through. That happens altogether too often. All right, so the AccelNet program, as Cornelia has already mentioned, it is intended to provide these linkages for international networks to come together and cooperatively identify and coordinate those efforts, specifically to address knowledge gaps and research needs to tackle grand research challenges. And certainly the area that you are all involved in is a grand research challenge that requires significant international coordination and collaboration in order to make major headway. By creating these linkages, we're, as a program, attempting to meet the goals of accelerating the process of scientific discovery and preparing the next generation of US researchers for these large-scale multi-team international collaborations. Science is becoming increasingly international and increasingly large scale in the teams. So we know that that requires some specific focus on how do we do that. It is an NSF-wide program, and I have listed colleagues from across the foundation who do include Soo-Siang. All of the directorates are represented in the program, and we feel delighted to be working across the foundation and identifying together areas that really do warrant the support for driving a field ahead by creating these new international linkages and strengthening those international linkages that have existed to be able to tackle grand challenges. The emphasis here is on supporting the connections not supporting the fundamental research. And that's why I'm also talking with several of my colleagues here who do actually support the research efforts, because we want the networks to come together, identify what are the roadblocks that are preventing scientific advances, and then to figure out how to address those roadblocks, which will mean that they will need research funding to carry out their projects that are developed after the coordinated efforts. So the current solicitation for AccelNet has a deadline coming up in October. We anticipate that we will fund, say, 10 to 14 awards. We have slightly modified the solicitation as it stands now. It supports design track, which are efforts to enable very early stage networks of networks to develop operational links, and then larger scale 5-year efforts to really implement that coordination. There are a wide variety of characteristics that we hope to see networks of networks develop, and the leveraging of resources for mutual benefits across the various international network partners is probably the most important that I will address here. I will use this slide simply to segue to say that once those networks have coordinated and identified where the research could go, it will be the research directorates across the foundation that will provide the support for those research activities. And so with that, I will segue to Grace.
Hello, next slide, please. I am Grace Wong. I am a program director from the Engineering Directorate in the Chemical, Bioengineering, Environment, and Transport Systems Division. I am a rotator from Johns Hopkins University, and I've been at the foundation for about 10 months. And this is my first Telluride. I actually checked in yesterday and watched Terry Sinowski's history of Telluride, and I'm delighted to be here and to see that the NSF has been supporting this Telluride workshop for, I think, 26 years. And I'm also thankful to Soo-Siang for allowing me to tell you about this wonderful opportunity that is a competition that's hosted by NSF's Emerging Frontiers in Research Innovation Program once every 2 years. And well over 200 submissions globally are submitted, and all ideas are reviewed and selected by an external advisory board. And the criteria for selection is based on the timeliness of the topic, whether it addresses an important national need or unsolved grand challenge, and whether or not it is multidisciplinary and has a community that is poised to respond. So it is my delight that this topic, brain-inspired dynamics for engineering energy efficient circuits in artificial intelligence, was selected as one of the 2 topics that will run this coming fiscal year. The solicitation has not been released, so I could tell you a little bit about historically what these programs look like. Each topics historically is given $30 million, and they're run typically over 2 cycles. The specific awards are what we call mid-scale, so that would be $2 million over the span of 4 years. And the expectation is that there would be 2 cycles. This year's topic was inspired by the computational and data efficiency of the brain. I was motivated by the fact that AI today, such as GPT-3, these big models, they require tons of data, lots of power, and yet they're not nearly as sophisticated as the biological brain that only requires approximately 12 to 20 watts of power and can learn with extreme energy efficiency, data efficiency, flexibility, and do so continually and learn causally from just a few examples. and do so at a fraction of the power budget if the same number of transistors were to be implemented on a standard CMOS chip. So next slide. And so what this topic looks like is on this page. This is part of a press release that was published in April, and you're welcome to take a snapshot of this page. The actual solicitation will be slated to come out later this year. And instead of reading the slide to you, I will say that some of the things Terry talked about in his introductory remarks yesterday about the importance of NeurIPS and the convergence, the 2012 convergence and the initiation of the BRAIN initiative. Wonderful story of, I won't spoil the story. So if you didn't watch his talk, I would recommend you watch it on YouTube. It was great. But the main idea is that we're learning so much from the brain, partly because of Obama's BRAIN initiative, which is largely an engineering project in the service of neuroscience. BRAID wants to take advantage of the wonderful insights that the BRAIN initiative is teaching us now that we have the technology to measure millions of neurons from the brains of awake and behaving animal while they're performing different tasks. What are their secrets, tricks is the brain up to that we're not aware of? So BRAID is about learning from neuroscience in the service of engineering, of AI, and in particular, engineered learning system. As you will see in the third bullet, there will be 3 focus areas that will be announced in the solicitation in the general area of theoretical neuroscience, brain-inspired circuit design, and algorithmic learning. And the hope is to reciprocally, cooperatively, and ethically advance foundational knowledge for future advances in engineered learning systems. If this sounds interesting to you and you want to make sure you're on the mailing list when the solicitation is released, please send me an email and just put the title BRAID mailing list with your name and your institution, and I will make sure you are on the mailing list. Next slide, please. So there are other programs in the engineering directorate that also supports neuromorphic engineering, and one of them is My Machine and Motor Nexus. Bob Scheit is the program director who you should contact if you're interested in M3X. Next slide, please. And there are other additional programs such as the CRCNS, which has been around, I want to say, for 20 years. And the next due date is November 23rd. The Integrative Strategies for Understanding Neural and Cognitive Systems, or NCS for short. The next due date for that is on February 14th, and there will be one more on the 15th in 2023. And the program that I run in the engineering directorate, Disability and Rehabilitation Engineering, also supports neuromorphic engineering research. If you're interested in submitting something to my program, it is best to send me a one-pager and to make sure that your idea is in scope before writing the entire 15-page proposal. It saves all of us time. And there are additional programs that you can check out at this link in the middle here of the page, and to learn more about other opportunities that fits with your research. So with that, I'm going to turn it over to Soo-Siang.
Good morning. Thank you, Cornelia, for this invitation to speak at Telluride. It has been a great pleasure to see sort of over the years, the evolution, the growth and expansion of this workshop. From its early days that was focused on sort of the development of sensors and computing hardware to the more current development of bio-inspired frameworks for processing and learning complex tasks. Internal to NSF, this trajectory of interest of the Telluride community also aligned well with the NSF's establishment of science of learning investments. And these investments started with the Science of Learning Centers in 2003 to advance fundamental knowledge about learning through integrative, interdisciplinary approaches. and then to use this knowledge for the advancement or to address societal challenges, which include innovations in technology, as well as how this fundamental knowledge about how people learn could inform learning and educational practices. So this is a very good alignment of Telluride's efforts with the program. And through the years, Telluride has been supported through the Science of Learning program through its various iterations, from the Science of Learning centers to the Science of Learning collaborative networks, and where Telluride also has an award from that framework. And then I want to talk today about the latest pivoting of the priority, Science of Learning priorities, to also include the idea of augmented intelligence. So the new name for the program is now Science of Learning and Augmented Intelligence. And the good news for this also is that this program is now a core program within NSF, which means that for the foreseeable future, there will be deadlines, there will be target dates for which interested applicants could send in their submissions. So so there will be a home for this kind of research. So I also want to mention that the first investments in Science of Learning also incorporated the Telluride workshop into our portfolio. And two of our centers actually have themes that are very relevant to this workshop. And these are these themes are temporal dynamics of learning, which with the leadership and members of that center are also part of the Telluride group. And then we also have the Celeste Center, focus on sort of multimodal approaches to the study of real-time autonomous learning. And that center was at Boston University. So what I want to do now is to talk about this program. So the whole notion of trying to understand learning is still part and parcel of this new Reposition program. We make more explicit, however, the program will support potentially transformative research that develops basic theoretical insights and fundamental knowledge about principles, processes, and mechanisms of learning. And the second part talks about augmented intelligence, and we're also interested in how human cognitive function can be augmented through interactions with others, contextual variations, and technological advances. Now, in terms of the kinds of projects that this community might be interested, we're very much interested, again, to repeat as Grace's talk indicated, the kinds of biologically inspired efforts to inform sort of artificial systems of learning. But we're also very interested in how these artificial systems can tell us something about how humans learn and about human cognition. So it's not just the one way, but both ways in cycle. And so we hope to get some of your interesting ideas to the program. And the way to do this is to send 1 to 2 page description of a project, send it to me. And if it is not appropriate for my program, we will try and send it on to the other programs. And if it is appropriate for my program and other programs, what I will do is then invite a co-review of the proposal with other programs. So to end, I want to just make a couple of comments to note as was often mentioned, that the Telluride workshop has been a longstanding effort supported by NSF. And I want to emphasize that we're not really, we're not sort of in the habit of funding things very long term. We like to sort of fund new things. And the success of Telluride, a key success of Telluride, is Telluride's ability in being able to adapt and to be flexible, and also coming up with models of successful leadership transitions and allowing the newer generations to be the drivers of the new intellectual directions of the workshop. That has been key to why Telluride has been supported by NSF. And it's also vitally important that Telluride increasingly has been more inclusive of other disciplines, including not just neuroscience, but the cognitive and behavioral sciences as part of the new thinking about how this field may move forward. And we also look to where the trainees are being placed, and how successful they are. And you have a record, excellent record of being able to place the trainees in a diversity of areas. So these are things that we look to. The fact that Telluride has been supported for so long is that you've been able to keep your eye on the North Star, keep your original vision, but also reinvent yourself in new ways to adapt to what is happening out there at the leading edge of science. That's a very important part. And I want to also comment that as we look to the Telluride workshop and its participants to be active players, and you're very well poised to be active players in sort of the neuroscience AI revolution, that you take steps to consider very carefully the ethical implications of the work you do. So this is a very, very important part. I'm very glad to see that this is also part of the beginning conversations of this workshop, because I think this is going to be vital. So thank you.
Thank you, Soo-Siang. That was very informative. Thank you all, Claire, Grace, Soo-Siang. So now Guido will tell us a bit about how you will navigate the workshop and how you can collaborate actively.
Fantastic. All right. Well, thank you very much. So I'm Guido Zarrella. I'm the director of the Institute of Neuromorphic Engineering, which has been the organization which benefits from all of this participation and is very grateful for the support of the NSF over all of these years. We are really proud and excited about this diverse and inclusive community of scientists that come together every year, well, notionally every year in Telluride. And you can see behind me, I have, as Toby, I think, mentioned it, kind of a generic, stereotypical Colorado landscape. So I am located here in Colorado. I wish that we could have you all here with us this year, but I am extremely excited that the virtual components of the workshop have made it possible for us to kind of open up our borders well beyond, the traditional levels of participation that were possible in the past. And so I anticipate going forward that if, given a successful outcome from this year's workshop, I expect and anticipate that many of you will be able to continue your participation, and we can keep growing this community with your help over time. So I'm really grateful for that. I also want to, before we kind of dive in, I want to thank the commercial sponsors that we have as well. This year, Sony AI, as well as Neurotech Foundation, have been very helpful in sponsoring the workshop in addition to the support that we received from the NSF. I want to point out that every dollar that comes into our organization is used to explicitly to host the workshop, and particularly for scholarships for student participation. And so we're very grateful for the support from these organizations. I know that Sony is doing some exciting things in this space, and you'll get a chance to hear from them during the course of the workshop as well. But going forward, we're eager to partner with organizations who share our values and our commitment to expanding the many fields that go into neuromorphic engineering. And so I just want to make sure I say thanks for that up front. We also have a lot of logistical support from important organizations that have been historically essential to this workshop and remain very, very important, and that includes the Salk Institute with Terry's participation there, Johns Hopkins, ETH Zurich, University of Maryland, and the MITRE Corporation are among those organizations. And as we kind of expand our leadership circles into additional, as we heard earlier, into new generations, and as we bring many of you into the organizational circles of this workshop, we expect that stuff will continue. And then, of course, the general chairs of this year's workshop, Shih-Chii and Emre, are obviously essential. They manage the technical program here, and so you'll be hearing a lot from them over the course of the workshop. We're really excited about what we put together. What I want to say is that we have a really unique community. This is the thing that has been kind of the defining characteristic of Telluride's success over the years is that in addition to being a learning and teaching community, which we certainly are, we're also one that fosters a hands-on participation. And so the collaboration that occurs in the labs in Telluride this year is going to be a very important part of the workshop as well. So we have a great lecture series lined up over the course of the next week and beyond. We expect a lot of dynamic conversation to come from that. But we also really want to strongly encourage everyone to participate and to get your hands dirty with some of the hardware remotely, with some of the software techniques and learning technologies, and bring your ideas into the community and help us understand how your research can support growth of this field in exciting new directions. So there's a lot of infrastructure that we've set up in order to make that possible. The bedrock of the collaboration component of this workshop is going to be our Slack community. So if you're not a member of the Slack community, please do join as soon as possible. Not only will you be able to ask questions and give feedback in relation to the talks that you see, but also you will have a chance to kind of join the many different discussion groups and the work groups that are going to be making the actual collaboration possible going forward. You'll find that there are channels for each of the technical topics, and then there'll be a lot of breakout groups. You can expect that there are a lot of other resources that we can make available to you here. So that includes access to hardware, things like low-E heat chips, analog, computing devices, all manner of different interesting pieces of hardware being brought to the table. We got a really exciting technical program this year. And so join the Slack, get into the topic groups, and then the topic leaders are going to be really helpful in getting you those additional technical resources so that you can participate and make exciting things happen. And then last, but certainly not least, I want to point out, I want to direct everyone to the code of conduct that we have on our website. This is an area that we take very seriously, and so this is a very inclusive and diverse community. And one of the things that comes with being a workshop is that everyone is bringing unpublished ideas, kind of cutting edge thoughts to the table. A lot of unpublished ideas might be presented here. And so I just want to make sure that we kind of underline that the outcomes of this workshop, we expect, a great outcome is if you find new teammates, if you do exciting work and, potentially end up publishing a paper together. We want to make sure that everyone is aware that, there's a lot of informal discussion of unpublished ideas, and please be respectful of people's, rights to that. And so ask permission before you kind of take anything and run with it. And then, of course, we have zero tolerance for any forms of abusive behavior or anything of that nature. The website clearly spells out all sorts of information on that topic, as well as how to report things if you feel that there's something that we need to address. So I just kind of want to make sure everyone's aware of that. I don't expect any problems in this awesome community, but we certainly will address them as we need to. So, so just let us know how we can help you. But with that, I really am very excited to kind of launch the technical portion of the 2021 Telluride workshop. This is always my favorite time of year. I know that all of our organizers feel exactly the same way. We're really excited to have you all here. There's great things ahead. And with that, I'm going to turn it over to Shih-Chii, who is going to take us on a journey through some of the history of the field and some of the ways that it's adapting and changing into the future. So thanks.
Hi, thanks, Guido. And let me see if I can share my screen. Yep. Okay. Can you see my screen?
Yes.
Okay, thank you. All right, so I'm going to go ahead and talk about. Sorry. Right, I'm going to talk about introduction to neuromorphic engineering. It's something that I talked about last year, but last year I talked more about the. One second. Right. So last year I talked more about historical perspective, and if you're interested in learning more about it, I put the link down here. But really what I want to talk about today is about the current state of neuromorphic engineering, the kind of exciting, interesting research directions, and also the future of where it could go. And so I think everybody is very motivated about the kind of efficiency that you see in biological computing systems. And it's got a very particular kind of architecture, which is very different from a computer. So we get a distributed compute and memory architecture that's very power efficient. The brain burns about 10 to 15 watts. And yet without writing any program, the brain is able to create or produce natural systems that exhibit complex behaviors such as pattern recognition and navigation and communication, even in a very simple insect like the bee. And so the question then is, can we come up with a new kind of technology that captures some of this inspiration that you see in brains? And this is something that Mead is a founder of this particular area called neuromorphic engineering or neuromorphic electronic systems. In fact, he wrote an article back in 1990 where he laid out his ideas of why he thought this would be a new interesting field for the future. And so I laid down here a couple of observations of what he had in the paper. I think you should read this paper, but it's a very interesting paper. And one thing that he noticed was the energy efficiency of computer systems in 1990 was 10 to the power of 5 ops per joules versus that of the nervous system. You can compute it, and it's 10 to the power of 12 to 10 to the power of 15 ops per joules. So it's more than 7 to 10 decades of order off. And the other thing was that compute energy can be reduced by representing information as relative values of analog signals. And it's cheaper to do certain basic operations using analog circuits rather than digital circuits. And finally, you could use organizing principles from the brain. Some nonlinear amplification is something you do when you're making decisions at different layers of the processing, including adaptation and also learning into the circuits. And so, of course, one of the most interesting and also well-studied systems is the retina. And so here you see a spatial temporal design of the retina from Misha Mahawal and Mead back in 1988. And this is on the cover of Scientific American. And here you can see that the retina captures the sort of age detection properties of cells in the retina. So you can see the outline of the cat. And then there was subsequently a much more detailed model of the retina just done by Zagul and Kwabena Bohan back in 2005. And so here you can see that he and Karen Zagul modeled circuits or implemented circuits that model the different cells that you observe in the retina in both the outer and inner plexiform layers. And then finally, this is the probably the best known retina, which is a dynamic vision sensor, also called the DVS. And so here, this particular pixel captures only one of the functionality of one of the classes of the retina, which is looking for temporal changes.
And so this is the sensor that has driven a lot of research in different areas, including robotics and computer vision. And partially this was done because to make a very detailed model of the retina, you need a machines that you can get fewer pixels in a particular chip area. But if you want to get a higher resolution retina and to look for, and also to implement functionality that is different from normal cameras, this turns out to be a very useful property that complements normal cameras, right? So normal cameras will take frames, but here you're looking for changes in the scene. And so here you can see, even for a rotating dot stimulus, what you get are a set of spikes, and the spikes basically come from the pixels that see the dot moving past the pixel. Okay, and this is what we're using now to look for new algorithms that use the timing of information from the spikes. And this retina now actually has also led to the emergence of different companies that build these retinas, for example, Innovation, Prophecy, and also Samsung. So I would say it's kind of a commercial success that came out of the neuromorphic engineering area. Now the other sensors, and this is another one, is called the dynamic audio sensor. And what this does is it captures the functionality of the cochlea. So this is the hearing organ. And it's usually modeled as a cascaded set of bandpass filters. And so what I want to show here is the output from these different filters. Again, it produces spikes in response to sound. And you can see for the different rows, we have different channels that are sensitive for different frequencies. You see a set of spikes that appear whenever a certain sound comes in. And nowadays also there's another new type of sensor or modality, and these are touch sensors. There's going to be a topic area around this. And with the emergence of new materials, you can actually build now also touch sensors and also produce spiking outputs, which then become compatible with the kind of outputs that you get from the audio and also from the visual modalities. So the other thing that's really nice right now is that there's a whole suite of neural network hardware platforms ranging from this custom mixed signal ASIC chips that include learning capabilities, NeuroGrid from Corbena Bohan's group, where they capture or they implement very detailed models of a neuron, and also brain skills, where they also implement basically millions of neurons. And we also have designs that are time multiplex digital designs. And for example, here's Spinnaker, the Intel Loihi chip, IBM True North, and also even the kind of commercial devices of FPGAs. You can use them to implement different neuron models. And so basically you have the capability of taking the model that you're interested in and implementing on these different platforms, and to have an understanding of how well these models work on, say, the output of the DVS in response to a particular change in the scene. And so I think it's very exciting times that we have all this infrastructure ready, so you can actually try out different things. And along with it, over the last 20 years, there have been many circuits that have been built, mixed signal analog digital circuits. And with this kind of dictionary, we call it like a neuromorphic circuit primitive dictionary, you can implement things like similarity circuits, Mune-Tegal, nonlinear resistors, temporal derivative functions, adaptive filter, phototransduction, current biasing. So it makes it easy to sort of take the circuits together and they act like building blocks. And then you can design a new circuit that uses some of this functionality as needed. Now, what kind of neuroscience primitives can we implement on this spiking neural network chips? And so if we go back here now to this picture of a reconstructed set of neurons, which are colored in different colors here. So one thing that you can do, and which Ronnie Douglas and Kevin Martin did, was to come up with a much more simplified model, because it's very hard to imagine that you could implement a detailed neuron circuit for each of these neurons that you see here. And so what you can do is you can compile them together or combine them together into 3 blocks. So basically you have 2 excitatory blocks, which compose of cells in the layers 2, 3 and layers 5, 6. And then you have a class of inhibitory cells. And based on the reconstruction that they've done over the years, you see that there's a lot of interconnection between these groups of neurons, right? So there's excitatory connections between layers 2, 3, and 5, 6. And there's also a lot of connections between the inhibitory neurons going to the excitatory cells and then back to inhibitory cells. And from this, you can create the motif known as the winner-take-all circuit or winner-take-all network, where you have a whole set of excitatory neurons, and then you have a global inhibitory neuron and this is partially because there's 80% of the cells are excitatory and 20% inhibitory. And so this motif has been used in many different places. And also over the years, there's also the networks known as reservoir networks, mostly coming out of Wolfgang Masser's group and also Herbert Jaeger, where they have a pool of neurons with excitatory and inhibitory neurons, and you have random connectivity or learned connectivity within the pool. And then you have projections from the pool to a set of output neurons, which basically are used as, for example, if you're doing digit recognition, then these output neurons would then represent the different digit classes. Okay, and then you would have some form of learning on top of these connections. So there's another path that was followed, and I just want to show this example of a system that came out of a EU-funded project, which is called Caviar, back in 2009. And so really, this is where the dynamic vision sensor Retina was first designed. And so this is a set of chips that were built by different groups. So there was the DVS that came from the Institute of Neuroinformatics, a set of convolution chips that came from a group in Spain, Bernabe Linares Barranco's group, and then the winner-take-all chip, and then basically another chip that implements the spike timing dependent plasticity rules, where the neurons will learn different trajectories of a moving object. And so in this case, there was a ball, and then you would program these different convolution chips with different size kernels. And then the object chip or the winner-take-all chip would then decide which kernel best matches what you see in the scene. And then the learning system would then learn the trajectory of the ball or the moving object. And what I want to show you in the video here so this is in 2009, so it's more than 13 years ago, is that maybe the electronics and also the boards are much bigger than before, but I think all these ideas are there, and this whole system is in hardware, right? So there's no software that controls the flow of events going across the set of chips. And what you're gonna see is a short video about electronic stabilization. So there'll be two different size circles circulating around, and the idea is to place one of the circles in the middle of the picture each time.
Shih-Chii, you need to comment because they're not sharing sound.
Oh, sorry. Yeah. Okay. All right. Anyway, I guess I just understood from Toby that you couldn't hear the sound, but the idea is that you have these two circles over here, and you want to electronically stabilize the largest circle in the middle, which means that now you program the 4 convolution chips with the different size kernels. You look for this particular size circle, and then from the spikes, you can get the center of mass of the location of the circle, run the winner-take-all so you can clean up, right, where this location is, and then use it to stabilize the circle in the middle. Okay, so there's certain properties of the system that we need to consider. So first, how scalable is it? So if I need to make a network that's much bigger, is it easy enough to take this designs and then scale them to say 10x or 100x more neurons? How adaptive is the system? So in essence, we get this from the dynamic vision sensor from the Retina because it's adaptive to different lighting conditions over 10 decades. How programmable it is. So this is something that I think the learning rules that people have been looking at in neuroscience could become interesting, because you really don't want to come in and program each time, you know, the size of kernel that you're interested in looking. For example, if you're looking for a certain size ball, you don't want to go and program the system for that particular size ball, right? In fact, you prefer that the system figures this out for itself. Now, of course, there's different plasticity rules that people have talked about over the years. So we have long-term plasticity and short-term plasticity. And so some examples of this are short-term depression, where the weight of the connection decreases over time as you come in with more input spikes. So this kind of dynamics is usually very short. It's induced over fractions of a second, and the recovery time is over seconds. And there's long-term plasticity, which is induced over seconds rather than fractions of seconds. There are many mechanisms are involved here, changing the number of receptors, release probability, and there are a number of plasticity rules that people have used, having plasticity rules and also modulated spike timing dependent plasticity rules. And so here's a typical example of an STDP rule that has been measured in vitro, where the weight of the synapse changes depending on whether the pre comes before the post or vice versa. Of course, there have been many studies where people have embedded these rules into these reservoir networks and looked at how this kind of local learning could help determine the connections that's needed for, say, a network to perform well on a certain task. And so this process has been kind of slow, I think, over the years. And really, there are certain developments in the last 5 years that really speeded things up. And one of them is, well, let me pass this here, is deep learning, right? The whole area of artificial intelligence. And there's different network architectures, convolutional networks, recurrent neural networks, multi-layer perceptron, are also brain inspired. And there are also different hardware platforms for implementing these models, also for training them. And especially nowadays, you have GPUs, which really has evolved from just having just a single compute and memory block to now having multi-core blocks and with memory that's closer to the computing blocks. And you can implement these networks also on FPGAs, and you can, so this study that was done by a group at MIT, and if you take a network like VGG8, one of the vision networks, you implement a CPU, then you implement the same network on GPU and an FPGA, you can actually increase the energy efficiency, right? Going from the CPU to the FPGA. And the same thing too for a recurrent neural network and LSTM network. And what's showing you is that if you know exactly what you want to build, you can make a custom chip that implements the network, and you can actually increase the energy efficiency of the hardware. But with this deep learning also comes with this very useful set of tools where you can actually now train the network to do a task well. And so we've used this in the last few years. And then another thing that also has become very important in the last few years is that there are many more billions of edge devices that people are using in the world, right? And this whole area of computing on the edge has become very important. And so, for example, here in this audio setup, you would have edge devices that do very simple audio tasks like keyword spotting, speaker verification, voice activity detection. So this is a task where you can use very small networks. You can run them on these devices, which are resource constrained, also very low memory capabilities or resource. So basically, you can think of it a bit like how the brain has to deal also with understanding the world with a very small power budget, right? And not much resource. And I think this helps us to determine the kind of networks that you would need to solve this much simpler problems. And then if you do this kind of task on the device, then you can then determine when you should send, say, for example, your audio up to the cloud after you've determined that this person is the one that I'm interested in listening to. So first you could do like voice activity detection, determine if a person is speaking, then you can send the audio up to the cloud for the much more energy expensive computing that's needed. And there are many different domains here where you can use these devices. And one of the challenges that face this hardware architectures that implement either deep neural networks or spiking neural networks is memory. And so this is a picture of the kind of power and memory that's needed to compute even a simple thing, for example, computing the activation of particular neuron as a function of the weighted activations of the input neurons. And so what you usually do here is you store the activations on the chip, right, in SRAM. And then you store the weights on DRAM off chip, because this memory is, you can get a much denser memory using DRAM. And now if you want to say solve the activation of this neuron, which is a summation of the weighted inputs, so you do this through the processing element, and then you send out the value of the activation. And now if you look at the energy costs, normalized to the energy that's burnt in the processing, dissipated in processing element, the energy cost of fetching things from SRAM or from memory is much more costly. For example, if you fetch it from SRAM, it's 10x more than doing a logic operation. And if you fetch it from DRAM off chip, it's 1000x more. And so because of this, people have been looking at different types of emerging non-volatile memory technology. And so I show here 3 examples of different types of NVMs, non-volatile memory, that have been in mass production. So the STT-MRAM, PCM, and CBRAM. And so here in this performance metrics table, it gives you a comparison of, for example, how small these memory devices are. They're in the order of nanometers. The kind of multi-level states you can get from these different types of devices. So this could be useful in the network that uses this memory devices. The amount of energy that you need to change the bit value of these devices. So it's quite low in femtojoules. Retention time is very long. You can integrate them into 3D technology, and also the variability of the devices also varies from very low for STT-MRAM to moderate for the other ones, PCM and CBRAM. And there are groups that have been looking at how you can embed this type of devices or use them as storing the weights of, say, a connection of a multi-layered network. So in this case, it's 2 layers, right? And so here you see the CBRAM devices for the first layer, and then the set of devices for the second layer. And also you can use them as digital memory. So in this case, it's used as analog memory, but you can also use a digital memory. And this is also done together in a spiking network format. And what you see here on the bottom is actually a particular kind of CBRAM device that comes from the group of Dugyo Kuzum at UCSD. And it's a subquantum CBRAM device, which so means it's extremely small. And what they've done is that they've made a chip that includes 512,000 of these devices, and then they show that they can solve the MNIST problem. So this is a particular data set of handwritten digits. And so you can actually build a network that achieves a certain amount of accuracy, I think over 90% using these devices. Now, where else can learning come in useful here? So I think one of the most exciting areas is in the area of continual learning. And so here's an example of, for example, a 5-layer convolution network that we've trained on DVS events. And you guys know this game of paper, rock, scissors, right, that you play as a child. And so you can train this network to look at a particular symbol that a person makes. For example, this is scissors. And then the network would then show that the output of this picture is scissors. And once you've trained it, usually you can't learn any other symbols. But what you can do is you can learn on the last layer, and you can learn new symbols, right? For example, you can create a funky symbol that looks like this, or have 2 ears and so on. And what we showed in this paper yet, you can actually train locally the last layer of this network to learn these new classes. And this is actually kind of nice because, training the network takes a lot of energy and also takes a lot of data samples. And so if you can train on new things that happen without retraining the whole network, you're saving a lot of energy, and also you can increase the capacity of the network or the capability of the network to detect new classes or learn new tasks. And so this is one we are doing it. And if you now say, well, how can I implement this on SNN? Well, we have also developed a set of conversion methods that allow us to transfer parameters from ANNs to SNNs. But of course, the better thing is you could learn on the spikes itself. And this is another architecture or network where they showed that they can, again, program or first learn the network, the convolutional network through spike-based methods like Slayer. And then you can learn on new gestures using the DVS again, using another kind of learning rule called surrogate gradient. And then you can also take this spiking network and implement it on the Intel Kappa Bay, right? So I think this is a very exciting area where you can actually combine both the kind of the strength of deep learning in training large networks, along with the kind of brain-inspired learning rules, right? Where you can actually now use networks of this type on the edge. And finally, where's the future? So that comes with new circuits, new kinds of sensors, emerging memory technology, energy efficient network learning architectures, event-based asynchronous signal processing ideas, algorithms for continual local learning, and also event-triggered control. And you'll see these topics appearing in the different topic areas. They're going to run through the workshop. And we can see many application domains for neuromorphic technology, particularly for edge computing devices. For example, the event camera or the DAS, where you can do audio scene analysis, video monitoring, human-machine interfaces, mobile or wearable electronics, fast robotics, as you can see here, with the drones, and also neuroprosthesis. And so finally, I'd like to acknowledge the colleagues from Carver Meets Group at Caltech, the Telluride Neuromorphic Engineering Cognition Workshops, colleagues, Census Group, members at Institute of Neuroinformatics, also the National Science Foundation and other commercial companies that sponsored the workshop. Also for all these ideas that have developed pretty much over the last 20, 30 years, right? And ideas that come because groups of people got together from different disciplines and then thought of new ways of solving a problem, right? Thank all of you for listening. Thank you.
All right, thank you, Shih-Chii. So the next step is the presentation of the topics. In which particular order, I don't know yet.
I think we can go alphabetically, which is what was in the schedule. So that would be ANT. Right. ANT.
ANT, yeah.
Sure, I can take a stab next. Oops. Share this. All right. Hello, everyone. Video on there as well. Great. So yes. So I'm Terry Stewart, National Research Council of Canada. That's a government research lab in Canada. And for this one, I'm working with Jennifer Hassler at Georgia Tech. And for this particular topic area, we'd like to focus on analog neuromorphics, and in particular, focusing on tools and techniques, just because analog gets sometimes very far away from the sort of digital design that people can be used to. So the core idea is, hey, let's, if we're going to be simulating neurons, let's not have digital circuitry that's going ahead and implementing, doing some digital approximation using floating point math or whatever of some equations. Let's actually have the devices themselves do that underlying physics. Let's have the transistors and capacitors and current actually be the voltages and currents that are, that we're wanting to have be simulated. And the core idea is there is this massive increases in efficiency. Carver-Mead in 1990 was, guessing that sort of thing could at least do 10,000 times. That's been shown. There's some situations where it's like 10 million times more efficient. So there's a huge range to go there, but there's also some giant disadvantages. One giant disadvantage is that it's just a completely different design process and different design methods than people are used to with digital. And then that also means that there's a definite lack of tools. So certainly the tool development for analog design is nowhere near as advanced as digital design is. Just way fewer people doing this. So that is sort of the emphasis of this workshop, or sorry, of this topic area within the workshop. We want to spend some time understanding this underlying theory, understanding these advantages and disadvantages of analog versus digital. We want to give people hands-on experience with working with analog neuromorphic devices. Of course, given that we're a virtual workshop, this will be all remote access. But we do have, Jennifer Hassler has developed these field programmable analog arrays, which are basically like FPGAs, but they're programmed, instead of being digital, they are analog, or combining aspects of both. I was also one of the developers on BrainDrop, which is a mixed analog digital neuromorphic chip, developed by Cornelia out of Stanford, and other people. And so we will also have remote access to that. In particular, we'll also be looking at, well, what are the existing tools for these things? What tools do we have for working on both of these? Some aspects of these are the sorts of the design tools that you're seeing there. I was also one of the developers on Mango, which is meant to be a really high-level design tool that is meant to, describe things at an extremely high level and then compile down to different neuromorphic hardware. So that's currently the way that we program BrainDrop. All of these tools have limitations, and one of the big things that we want to look at is, all right, what's needed, what improvements are needed to these things? Can we, as part of this workshop, work on improving these tools, or can we at the very least describe, well, what improvements would be needed to these tools? The way that we're going to do this is we're going to start week one on here's a bunch of videos to watch, some papers to read, some little assignments to do, and then every day we'll have a discussion period basically after the main sessions, and where people can talk about what they've read and assignments they've done. That will get us the background in FPAAs and in Mango itself for doing these generic high-level tools. Week two, we'll start getting into more specific, okay, how do the principles that we've just learned, how do they feed into BrainDrop? Let's start doing hands-on projects with FPAAs. I think we also want to have some interesting discussions on this aspect of remote access to hardware, which is becoming more and more important. People are building hardware all over the world, but then no one can access it except your lab. So that sort of generic question of making that hardware access remotely. And then figuring out, what projects do people want to work on based on the interest of participants. The sorts of things we have, in mind are, well, on both FPAs and BrainDrop, we can do things like taking basic neural network circuits and going and implementing them. So doing function approximation, doing categorization, keyword spotting, tasks like that would be sort of in the right ballpark of what we can do. And then also projects improving these tools. And that's our plan. So please come join the ANT Slack channel, and looking forward to talking with you. Thanks.
Okay, great. But just remind everybody here's here to ask questions of the speakers. I see some questions for Shih-Chii already on the hash questions channel of the Slack. So keep them coming, and then the speakers can answer them offline in the chat. I guess I'll take over now with LTC. Is that okay?
It's your turn.
Go for it.
Okay. So the Learning to Control 21 challenge is all about learning dynamics from control data with machine learning, and then doing optimal control with model predictions in the context of model predictive control. And this is led by myself and Manfred Marari, who is the person that really invented model predictive control in the context of chemical plant control decades ago. We have this nice expert panel here of experts from various divisions of control, and we have this set of invited speakers I'm going to tell you about later. But this whole thing has been put together by a team working for essentially the last year. Since the last workshop, we've been meeting weekly to continue working on projects that we started last summer. And we've been working quite hard to prepare for this year. I'll tell you about some of those.
I'm not sure if you're sharing a presentation, but we're seeing your desktop here.
Oh, thank you for that. You should tell me sooner. Tell me sooner that I'm sharing the wrong screen. Yeah, so I'll have to start over then. Yeah, I'm sharing the wrong screen entirely. Okay, so I just want to show you now that this challenge is about learning dynamics from control data and optimally controlling with model predictions, organized by myself, Manfred Morari, with this expert panel that's going to meet and discuss the presentation from Ugo on Wednesday. And then we'll have a couple more presentations I'll tell you about. And this whole thing's been a collaborative effort over the last year since the last workshop of all these people meeting weekly in Zoom meetings. I'll tell you first about the two invited talks. The first one is about learning how to autonomously race a car. If you want to learn how to autonomously race a car with a predictive control approach, come to the Wednesday presentation from Ugo Rosolia from the Amber Lab at Caltech, formerly from Francisco Barella's group at UC Berkeley. Here, just watch this video. This is the first lap. You can see the car is sedately driving around. This is a desert track, sedately driving around like a learner might do. And then after just a few laps around the track, if you hear it here, I don't know if you hear the sound. Yeah, it's sliding around the track. So if you want to hear about how to do that, come Wednesday. And then on Friday, there'll be a talk about learning quadrupedal locomotion over challenging terrain from Junhoo Lee at the Robotics and Systems Lab at ETH Zurich. Come and hear how he used reinforcement learning and transfer learning simulation to get the RSL, the Robotics and Systems Lab animal, to walk over these extremely challenging terrains with bumps, various levels of slipperiness and traction. It's really quite impressive work. I think a lot of people here are going to be interested in that. And then next Wednesday, we'll have a talk from Sebastian Trimp in Aachen on lessons from using ML for control. He's going to show some things that they've done, combining machine learning with control, and answer questions from the participants in the channel who will learn a lot from this practical experience. Okay. Now, the aim of this LTC 21 topic area is kind of exemplified by this artificial race car here. This is the Learning to Race platform. The thing is, can you just drive this car by hand or by some algorithm, and then by observing the dynamics, learn something about how the dynamics of this actually quite complex model works? What is the underlying dynamical system equations? Can you learn that in a model? So we want to explore methods for system identification with machine learning, for example, deep neural networks. We want to then do control based on the prediction of future states of a system with a method like model predictive control combined with model predictive path integration. And then finally, we'd like to join these two things together, combine the two parts for state-of-the-art control of a dynamical system like a car or the classic cart pole system. We want to discuss the use of AI hardware acceleration for real-time optimal control. In fact, this was the original motivation to start this topic area, because we had developed neuromorphic hardware accelerators that will allow us to do very quick inference of deep neural networks. And now we want to combine that, instead of just doing perception, classification and stuff like that, we'd like to combine that with real-time feedback control to do optimal control, ultimately. And so, but why do we want to learn a model? Well, it's for doing nonlinear model predictive control in conjunction with model predictive path integration. If you don't know what that means, the idea is really quite simple. It came from the work on the Auto Rally project at Georgia Tech. Here you can see it actually predicting the future consequences of particular control actions, throttle, steering, and brake on this outdoor race car. And by rolling out thousands of these predictions per time step and averaging them properly together, you can numerically compute an optimal control action so that this car is able to keep up or even drive faster than the best human drivers around this racetrack. I think this is just a beautiful demonstration of stochastic estimation of optimal control. And it's what inspired us to start the workshop, and it's what we've been working on since the first time last year. But actually, we started this topic area to bring control back into Telluride in 2019. And we demonstrated in 2019 recurrent neural network control of a hybrid dynamical transfemoral prosthesis, this electronic leg here, with the EDGE Delta Recurrent Neural Network Accelerator. Rachel and Chang led this project. Here was the whole project team that year. But the idea of this project was the first work to use a hardware accelerated recurrent neural network for real-time control. And you can see it here. Rachel is walking up the street at Caltech. This is the E-leg controlled by proportional derivative control, which is keeping the knee and ankle joint of this leg on a desired trajectory, which is actually learned from human data. And this is the same control being executed by the recurrent neural network. And you can't tell the difference here. This is just a preliminary step because we weren't really doing optimal control. We were just generating the control here, mimicking, trained from data collected from this controller. We were mimicking the control with the RNN controller. But the point is that we were doing that with a recurrent neural network accelerator that's kind of spike-based. It sparsely updated the downstream states depending on the activation change in the neurons. And this is the EDGE Delta Recurrent Neural Network Accelerator, which runs on a $90 FPGA, which is actually sitting on the E-leg here. It burns only a couple of watts, and it's 50 times faster than a Raspberry Pi to execute this. So that's what got us going on this whole control topic. Then in 2020, we went virtual and we wrote this L2 race platform. It's an internet virtual driving racing game. We got out our joystick controllers, we collected a lot of training data, and we tried to do system identification with a method called SIND and also with deep neural networks. And the culmination of that last summer was this tricontinental race between humans. You can see how ineptly they're driving, and the computer algorithm, I think, which actually easily won the race at that time, even around this simple track. By the way, you might wonder, why are these humans so inept at driving this car? It's because of the steering delay. When you try to turn the steering wheel, it takes substantial time for the steering actually to turn. And your control systems, and it turns out humans are actually very bad at dealing with these time delays. So these cars are actually quite difficult to drive, even though they're practically are not losing traction at all here. So we have a ways to go here. Since the last workshop in 2020, we developed this beautiful cart pole simulator. I have to say a word. You might think that the cart pole is kind of a solved problem. It is in some sense, but it's also still a very interesting problem because the cart pole is a prototype of an under controlled system, under actuated system. You're trying to control 2 degrees of freedom here, the angle of the pole and the position of the cart, with 1 degree of control, which is the force on the cart. So it's kind of intrinsically interesting because those are conflicting demands. And so it's still continually interesting. And watch one of our tutorials videos, and you'll see all the applications of this, even of the cart pole, for real control systems, like controlling rockets when they're descending from space. So we have this cart pole simulator, and from this cart pole now we can collect training data and develop a multi-layer perceptron or a gated recurrent unit RNN to predict the future states of the system, in this case, the angle of the pole, as a function of time in response to the control input. And here you can see the rollouts. The rollouts are the predictions of the network over time, fed back recursively. You can see the rollout here as this colored curve. And you can see this MLP here. It looks like a GRU, small recurrent neural network with maybe 100 units in it in total, which is predicting the future state of the system in response to the control input quite accurately. In this case, trained from a small amount of training data. And using this, this kind of prediction, now we can do this model predictive path integration rollout. So you can see here now, again, you have the position and angle of the cart pole as a function of time. And these green traces here are the different rollouts with different control actions applied. Now we can average those rollouts together and get the red control plan here and just pick the first one. And then we can attempt to do things like keep this pendulum vertical, the pole vertical, and follow a desired trajectory, which is this dark curve here. What it's actually achieving is the green curve. So it's not very optimal, but at least it's stabilizing the pendulum so it does the pole, so it doesn't fall down. And now we're starting to apply the same techniques to this virtual racing game. And so we think this is very interesting for future control systems where it's difficult and painful to develop the dynamical system models. The reality is always more complicated than any differential equations you can write. And identifying the parameters of those differential equations is also extremely difficult. So we're hoping it's probably a vain hope, but we're hoping now to use deep learning technology to ease the pain of developing these dynamical system models. And so we have a number of smaller and larger projects in mind for the learning to control topic area this year. For example, for the purpose of dynamical systems modeling, is a gated recurrent unit an advantage? Can we adapt to parameter changes thanks to its memory? You know, it's an RNN, so it has a kind of a short-term memory. And for example, can the short-term memory units learn from a small amount of data what the friction of the track is? Is it a snowy track or is it a dry pavement track? And can it adapt the dynamical system based on that? Can we get better prediction accuracy with the GRU than with a multi-layer perceptron, which is stateless, with the same number of trainable parameters? This is the kind of experiment that a student could actually do in a short amount of time. How do we deal with control data imbalance, which is a big problem because most of the time all your samples are from a very small part of the space or little control data. Always a big problem with real systems to get enough control data to train on. Can we do clever optimizing of the model predictive control rollouts? For example, can we improve our results by using gradient information collected numerically for the model predictive path integration? And can we do early stopping of high cost rollout computations? For example, if we're doing a rollout and the car crashes, we can just abort that rollout early. Don't bother going on further with it. Using the real cart pull, because we have physical cart pull for participants to play with remotely, can the deep neural network model time delays and unmodeled noise and nonlinearities, which are not captured in the dynamical systems equations? Those are the kinds of questions that we'd like to ask. We have many more such questions, and please join our LTC channel and our topic area meetings. We welcome your participation from complete newbie to control expert. And check out our tutorials, please. Thank you. Okay.
Cool. Thank you, Toby. So our next topic is going to be Gert and Rodolphe with the neuromodulator recontrol.
Okay, so hi everyone. So let me share the screen here. Okay, so this is about neuromodulation control. So this is really a interactive work group here, where we're exploring principles of neuromodulator robust control and learning using continuous time analog neuromorphic hardware. Right, so we'll take participants here through different steps of modular design methodology, right? Going from spiking neurons, small subcircuits, to more complex assemblies with bursting neurons in small networks, and then to synthesize complex neurodynamics, right? So, patterns of rhythmic behaviors in central pattern generators. That are close to what is happening in neurobiology. And so we'll be doing this in software, but then also transitioning to actual hardware. So we have continuous time analog hardware available to participants here, right, where we can demonstrate, owing to these principles of neuromodulation at different levels in the stack here, demonstrate robustness not only of the dynamics of these generated networks, but also robustness to variability and uncertainty, both in the environment and also intrinsic to the hardware itself. And so we have an expert panel that will be addressing fundamental questions. We'll go over that because on Wednesday here. Let's focus here on some of the tools that are available to the workshop participants, and also what the challenges that we're addressing here. So we're using here NeuroDyn, which is a neuromorphic platform. This is basically continuous time analog neuromorphic hardware that features 4 generalized Hutchinson-Huxley neurons, so spiking neurons, with 12 conductance-based synapses. And this really adheres to the fundamental principles of physics of computation that Carver Mead taught us when the field of neuromorphic engineering started right, with close physical principles that cross from biology to silicon. And so naturally, this analog hardware will have the same types of properties as what you have in biological systems, including also effects of mismatch. So what you design is not what you get. So there's lots of variability, and that has to be accounted for. And that's part of the challenge here that we have to address. But also there's great opportunities because you can get great efficiency and great resilience through basically a proper design of the architecture and the principles here. So, and the Neurodin hardware, while it is internally continuous time and analog, it is externally digitally programmable. So as participants, you will have a great flexibility in configuring the massive amount of parameters. We have basically 384 digitally programmable parameters that govern, that control basically all the features and the network properties of this of Neurodin here. So we have available for the workshop is a system with we call this NeuroCube. Is basically 4 interconnected Neurodin chips. So together, this will have 16 neural compartments, 96 gating variables, 48 chemical synapses, and through the coupling of those 4 Neurodin chips, we'll have electrically, so we'll have 24 electrical junctions, right, between those neurons, and a total of 1,560 fully adjustable parameters. So this is massive complexity, of course, which adds to the challenge here. It's both a challenge and an opportunity to control and harness complex neurodynamics, and also take advantage of neuromodulation then in order to get a great resilience of this architecture. So each node in network can be fully accessed through voltage and current clamps or dynamic clamps. And you think of this system as really as if you had virtually 16 virtual pipette electrodes that you can stick in those 16 membranes here for characterizing the neural dynamics. And so as participants, you have remote access to that interface through basically through over Python. And so with that, Sodolf will tell us more about the some of the challenges here.
Thank you, Guido. So I will just add a few words on neuromodulation. I'm a relatively newcomer to Telluride. I'm a control theorist primarily, but I've become extremely interested in this topic of neuromodulation, which is perhaps a new topic at Telluride. And we very much hope that it is a topic that we'll be able to develop over several years. On Wednesday, we will have a talk by Yves Marder, who is really the neuroscience pioneer of studying neuromodulation and showing the importance of neuromodulation from the cellular level to the network level. And it will be a great opportunity to hear her speaking. And essentially the challenge this year will be mimicking the work that Yves Marder has been doing on the Lobster STG, which is a relatively small network, but already showing an incredible level of control. Next slide, please. So what we are going to do is to sort of replicate sort of a toy version of the STG network that Yves Marder has been studying. And what we want to demonstrate is one perhaps most important feature of neuromodulation that is now start being recognized in machine learning, in control, and which is providing an entirely new way to do multiplexing when you do network control. And so we are going to play with in this case, a 5-node network. So it's really a very, very simple network. But we are going to show that by neuromodulation, you can change the function of this network in a combinatorial number of fashion. And we want to demonstrate that first in software and show that the control principles behind neuromodulation are fairly simple. And then we want to demonstrate that in hardware. Next slide, please. And so what we are going to do is to propose a neuromodulatory design constrained by a particular architecture, in particular the NeuroDyn architecture that Gert just talked about. And we are going to show that we can, using the building blocks of this NeuroDyn architecture, which are essentially Hodgkin-Huxley types of models, of simple models of neurons. And just by interconnecting these simple blocks, we can mimic how the lobster creates this STG by creating bursting neurons from spiking neurons, and then by creating rhythmic boxes from interconnecting bursting neurons. And I think this sort of ties the challenges in the very first years of Telluride, but revisiting those early challenges in the scope of neuromodulation. And what we want to investigate with this hardware challenge is whether neuromodulation helps coping with the uncertainty of analog circuits, and whether we can demonstrate this multiplexing function that Terry Sejnowski will also illustrate in his talk next week on neuromodulation. And then in the third week of the workshop, we will have a talk by Guillaume Drillon showing how you can apply this in machine learning. So I think it's going to be an exciting challenge, and all the instructions for the first week are now available on Slack. And so please join on Slack to join the challenge. Thank you.
All right, thank you, Gert and Rodolphe. So the next is going to be Shih-Chii and Bodo.
Yeah, all right. So I'll start first and then Bodo will take over. Yeah, so anyway, this is the sensory motor integration topic area. So we have Bodo, myself, and Gerben from Donner's Institute, and also I running the topic area. And next. Okay, so here's the aim of the topic area. So we want to focus on event-driven models of sensory motor control for an agent in natural environments, particularly focusing on models that can extract sparse streams of information for enabling dynamic, efficient control. So we'll focus on sensory motor control models that incorporate knowledge from neuro-inspired visual models, deep learning models, example, reinforcement learning, and event-driven deep neural network algorithms. And so we believe this is an important step needed to advance neuromorphic technology towards cognitive models that can direct the low-level sensory processing in a behavioral task. And so so usually when the workshop comes around, we have different types of hardware that we bring. And so, for example, we have the spiking sensor designs like the DBS with a bunch of neural network hardware. And then we have also various kind of robotic platforms like the pencil balancer that you see here in the white platform that you see. Unfortunately, I don't have the cursor. Bodo, you can point to it if you like. Yeah, the pencil balancer. Yeah. It's actually one of the robot platforms that was done at Telluride. Okay, and then next. So what we want to do here in the topic area is to figure out what sort of features we should extract when you have to move around in a natural environment, right? So for example, one thing you could think of with the DBS is that you extract optical flow. And so here's a particular algorithm that was applied to the output of the DBS, where you can see that you can extract the flow of a car that's basically on the freeway driving towards the airport. It's a video shot by Toby and his student. Again, you can see it's a color wheel, so the different colors basically indicate the different directions of motion. Yeah, it's good. And so what I want to show is an example demonstrator that was done at Telluride 2016, and this is from Tiffany Wu and Jeff Pritchman's group. And then what they did here was they had a little car that was mounted with a camera, which is in the red box, yeah. And they also had the True North platform, the spiking network platform. And what they did was they trained a little CNN to basically determine which way the car should move, right? And so if you go to the 3 panels, yeah, right there, right? So you get a particular image, and then you have to decide whether you should move forward, turn left, or turn right. And so after they've trained the network with lots and lots of data, right? So Tiffany went and collected all these different images. So basically then they let the car go along this path that you see up in the mountains, this yellow path, right? So this is right above the town of Telluride. And what you're going to see next is basically this robot driving along this trail. Yeah, there we go. And so there you can see Tiffany. Oh, well, I think the video is kind of big jerky. Ah, there you go. Yes, you can see now the little robot with the camera. It's moving by itself, depending on what it sees. Yeah. I think Guido is there, isn't? Is that you, Guido?
Yeah, I think I'm in there somewhere. Yep.
Yeah, is that you with the hat? Looks like you from the back.
Yeah, I definitely remember the robot. That was a good one.
Yeah. It's cool. Okay. And usually we start ideas at Telluride and then we go back and we try it out in our own environment. But so anyway, this is another one I want to show. This is the predator prey robot where you see 2 robots, yeah, chasing each other. Well, one's chasing the other one. And the one that's chasing the prey has a DBS. And what you see here on the right is basically the output of the DBS, right? So you get the different colors, the green and the red, because those are the spikes for the on and off contrast changes. And then you also see like this vertical bar, this highlighted red vertical bar. And basically that's the output of the CNN, right? That's trained to tell where the prey is. So you can see when the prey is in the middle, then the bar goes red in the middle. Yeah, then when it goes to left, then it's left. Yeah. And so and you can see on the left, here's the video of the one robot chasing the other one. And this is just a very tiny little CNN that's needed to determine, how this robot should move around or catch the prey. And so the other thing is that the next example I want to show is the DBS mounted on a drone. And this is done in Cornelia Fermüller's lab. And again, this is something that there was some preliminary discussions at the workshop, but a lot of the work was done afterwards because you need a special space and so on. We did bring drones to Telluride before, but you don't like to be at that high altitude. So you usually have to do it within the lab. And so what you can see here, the drone has 2 cameras, 2 DBS, one's facing forward, the other's facing downwards. And basically they're objects that are thrown at the drone and the drone manages to avoid it. Yeah. And so you can also see the output of the DBS from the 2 cameras, right? So here from the top and camera, bottom camera, and in the middle, you can see the trajectory of the obstacle. And so basically the drone can determine when the obstacle is about to hit it and then avoid it. Yeah. And so for this, there was a special set of networks that were put in place to extract kind of the important features that are needed so that they could determine the trajectory of the obstacle in this kind of more cluttered environment. Yeah. And so anyway, this is something that we want to investigate further in this topic area. And Bodo's going to tell you how we're going to do this.
Right. Thank you, Shih-Chii. So clearly we've come a long way building closed loop sensory motor systems. But there's still challenges ahead. And in one particular aspect we want to focus on in this topic area is how we can move or go beyond this kind of reactive systems that we've seen here towards systems that are more able to plan ahead and agents that are learning based on sparse rewards as is happening in nature. And so to explore this further, we are looking at a very simple pipeline to begin with. So our goal is to close the loop between sensory input, action, and reward in a simple but hopefully naturalistic reinforcement learning task using brain-inspired components along the way. So this is what the initial starting point will look like. We have an agent navigating a maze-like virtual environment. and learning given sparse reward signals. And the agent takes as input visual signals, for instance, can be landmarks that indicate the fitness of a certain path. And it acts on these this visual input using a DNN as a feature extractor plus some reinforcement policy model. We are then going to extend this pipeline step by step, making it more and more neuromorphic. For instance, we will explore the V1net developed at MIT. We'll have 2 participants and team members from Jim DiCarlo's lab that are going to help us with that. And one cool feature about V1net is that it's been shown to be very robust to perturbations and adversarial attacks. And so we'll be able to test this together with the DBS later on. Another aspect that's nice about it is it comes with a metric called brain score that basically tells us how well the features that we have in the network align with real recordings from the brain. And so we'll be able to use this pipeline, this metric, brain score metric, along the way as we more and more adjust this pipeline and check what effect our modifications have on the kind of features or the biological realism that of the features that we are getting in our network. Another extension will then be to use the DBS as a front end to transform the frame visual input into a DBS event stream. And since we are virtual, we will be using the V2E tool developed at the Institute of Neuroinformatics for that. A further extension will be then to use a spike-based learning rule. Since we are dealing now with event-based input, for instance, we can use Layer or some third-factor learning rule that includes the sparse reward. And finally, we are targeting LUI as one possible hardware platform to deploy the network from. And this is, of course, challenging, but if we succeed, we'll have an end-to-end neuromorphic system that will be able to do cool stuff like online learning with the DVS or DVS emulator and LUI in the loop. We have a fantastic lineup of speakers that we've invited, and I'm looking forward to their talks on neurorobotics, on learning, bio-inspired learning, on modeling the visual cortex, and we'll have a set of experts in our panel discussion that will help us answer some of these challenges and get ideas and a vision for answering these challenges on Tuesday. We also have a fantastic team of helpers that will support the practical projects. And if any of this is exciting to you as well, then join us on our Slack channel, and we'll look forward very much to working with you on this. Thank you.
All right, thank you, Bodo. So the next is Tactile Group, Kara.
Hi, everybody. Can you see my screen?
I can see it.
Yeah.
We still see your editor view.
Yeah, I had the presenter views that was covering the show slides. Okay, so this is the last topic area, and it's about neuromorphic tactile sensing for physical interaction and understanding. So the first question is why touch? Why tactile sensing? Well, tactile sensing is the gateway for physical interaction. It's very important to feel the properties of objects, softness, roughness, weight, and so on. And so it's very useful for manipulation, but also for, together with other senses like vision and proprioception, to kind of build a concept of your own body in the space and how you can interact physically with the space that surrounds you. So why is this interesting in engineering? So, well, in robotics, and here you see one example of a humanoid robot that is equipped with tactile sensors. Tactile sensing is very important for grasping and object manipulation. and also object recognition. But it's also very important for physical human-robot interaction and safety. So you don't want the robot to move and crash against things because it doesn't feel the surrounding. Another very important application area is the design of prosthetic devices, where you can use tactile sensing to restore sensory feedback. And this is very important to improve the acceptability of prosthetic devices and to, let people manipulate objects with more confidence and in an easier way. So this topic, of course, is not just about touch, it's about neuromorphic touch specifically. And why is it useful to go neuromorphic when we talk about tactile sensing? Well, if you think about touch, you can also see it here with this small squirrel. The tactile sensing is very localized. It's localized in space and in time. Usually you have contact on a very small part of the skin for a short time. And so if you use an event-driven encoding where you send data only when there is a contact, during the contact, then you basically compress the signal and have an efficient encoding. And this is, from the engineering point, basically it helps in decreasing the data that you send around, that you have to store, process, and so on. It's very similar to the concept of the dynamic vision sensor, for example, but probably with touch is even more localized, and you can gain even more in the compression. It's important for improving the sensory feedback in prosthetic devices, but it's also a nice framework to learn about spiky neural networks, learning, and sensory processing. And well, neuromorphic, we also do it because it's fun, and that's why we are all in Telluride. So which projects are we going to work on during this Telluride? One is shown on the left, and it's the braille recognition. So this would be kind of the entry level of the projects, where we have pre-recorded data sets done with this nice setup, where we have spikes from the tactile sensors in the fingertip that you see sliding on top of the braille letters. And we can use an architecture with spiky neural networks to learn to recognize the braille letters. And in this case, it's really recognizing a temporal sequence of spikes. Then the picture on the right shows you the stimuli that we have built for the second project. That is, basically the goal is to do recognition of these 3D shapes. And it seems an easy task, but in this case, you don't only use touch, but you also need to control the robot in a specific way. So what you need to do is to basically do contour following or line following, and put together the information about the sensors, because you need the sensor information to follow the contour, and the control and the proprioception of the robot to understand or recognize the shape. And in this case, we kind of went a bit back to the roots of Telluride, where there were these line following robots that were doing line following with vision. In this case, we want to do that with touch. And so in this project, we're going to put together tactile for control, and then putting together the control information and tactile information to do the recognition. And if you're really, really good, then we can scale up this problem, adding, for example, texture recognition. And then the third project is, again, going to the roots of Telluride, thinking about some circuit design. We have some models of the resistive sensors that were provided by Benjamin T. And we already integrated those in SPICE simulations. So the idea is to develop event-driven resistive sensing circuits. And the tools that we are going to use are pre-recorded data sets You also have the ICAP simulator with the tactile sensors integrated in the hands, so that we can do more data sets and combine the tactile information with the control to run the full experiment. We're going to use PyTorch and spiky neural networks for learning. We have the possibility to use Loihi. And for the project on circuit design, we can use T-Spice. And in collaboration with the ANT, the first topic area you heard of, we can also try to use field programmable analog arrays. And so just in summary, the goals of this topic area is to learn about tactile sensory encoding and how to use spikes coming from tactile sensors, how to do tactile sensory encoding in hardware, and also how to do learning spiky neural networks in hardware. The questions we are going to work on is how to implement learning in spiky neural networks for temporal sequences and sensor fusion. So we have an amazing row of speakers. Nishtish will give tomorrow the first introduction on the topic. And we have Veronica, who's going to talk about tactile sensing in robotics. And then we have Alan talking more about the neurobiology of the senses, Hannes about spiking and encoding in tactile systems and how to model them. Stefano is going to talk about information theory and encoding and decoding in the brain. And Friedemann is going to support us and talk about learning in spiky neural networks. And Harold is going to talk about event-driven vision and tactile sensing. And last but not least, this is the team. And let me really thank the people listed here, because they really did a lot of work in preparing the tutorials and the materials and templates, Docker, things that you can easily download and install to be ready to run the projects if you're interested. And Elisa and I are the topic leaders. So if you have any question, if you're interested, just join the TAC 21 channel on Slack. And I also want to thank the New Touch project that I'm coordinating, because some of the students that are helping with this topic area, they come from this project, and they a lot of them also enrolled to participate to different projects.
All right, thank you, Kara. A beautiful lineup of speakers. So that was for all the topics today. So I just want to remind you also, so the main schedule is going to include lectures and panels, which are organized by each of these topics. But the actual hands-on work and that you would like to participate in is going to be organized through Slack. So if you haven't done that already, you should go in and join those Slack channels and hopefully quite soon get your hands dirty on working on actual hardware. Okay, the next item on our schedule is going to be Andreas Andrew, who's going to be holding a discussion on the ethics.
Okay, so thank you. Let me share my screen. You see my screen? I'll put the presentation. Is everything good?
Yep, looks good.
Okay, so first of all, welcome to Virtual Telluride 2021. Discussion groups at Telluride are non-structured, and I intend to really follow that tradition. That's why they're discussion groups. People get together, they think of something, and they sit down, or during a hike, or in a pub, have some meals, have some beer, and really take some notes and really take it from there and develop ideas, thoughts about a topic. However, in the spirit of a virtual workshop where we have to be a little bit more organized, we have, with the help of Terry, decided that we'll give 2 topics this year for discussion. Of course, other topics let me know if you're interested in discussing something else, and people join in. We'll have a Slack, we have a Slack channel already. And let me introduce the two topics. And the first topic is really related to ethics and social justice in neuromorphic science and technology. And this can be philosophical, but also can be very, very practical. And in the next slides, I intend to give a very practical example of things that we should be doing as community. And the second topic is really something that others and myself have been thinking. How do brains learn how to configure themselves, and how do machines do that? And I'm not talking about pruning of deep neural networks. I'm talking about learning how to develop an architecture to solve a problem. This is something that at some point or another, various people have worked at Telluride, including Rodney. I remember Rodney using this game of life type of simulation with some friends from Los Alamos to really see if he can get a cortical structure to develop, in some virtual environment. So anyway, let me begin with a practical example of social justice that we can really do in our group, in our society. And one step, for example, is really eliminate offending terminology in our devices, systems, code, papers, and reports. Everybody at Telluride have used, or at some point or another, a device that has a serial peripheral interface, often called SPI interface. And if you look at the terminology that has been adopted over many years, the terminology involves what the serial peripheral interface does. It's a clock interface, serial interface, where you can have multiple devices talking to a central unit. And so traditionally, the community has used terms like master out, slave for the signals, master in, slave out for the, again, for the signals. Instead of chip select, the community and papers and documentation have used slave select. This is really ridiculous. So let's try to use notation that is not offending. And for example, in this case, an output signal on a device where data is sent out to another SPI device is a serial data out. Conversely, if the data is coming in, it's a serial data in. Chip select is something that is specific to a device. Control allowed peripheral in is really a substitute for master out, master in, and controller in, peripheral out is basically equivalent to using SOSI, which is a slave out, slave in. There is an open source website that is really trying to make this become more acceptable and widespread. Please go there and also sign if you believe such changes should happen, your support for this effort. On a less practical and more principle, I suppose, topics, Steri, we plan to have a speaker come and give an overview, but at the last minute, we couldn't get him to, couldn't make it. So Terry volunteered to give a brief presentation of ethical discussions and social justice discussions in communities on learning and machine learning and whatnot. Okay, so Terry, I'm gonna let you take on from here, stop share, and you take over.
Sounds good. All right, let me share my screen. We're actually like a minute ahead of schedule. How in the world did that happen? I don't think I've ever been at a Telluride where that's been true. So anyway, we're normally way behind. All right, so hello everyone. So yeah, I want to start this with a bit of a disclaimer. This is not my research area. I'm not. I'm very. I'm very interested in the ethical issues in AI, but it's not something that I actively research. And the other aspect of that disclaimer is as I doing all of this reading, and it is incredibly clear that all of these issues that I'm about to talk about are things that affect other people way more than they affect me. So, I mean, I'm a white cis male in a fairly affluent society, native English speaker. I can pretend to be straight if I really, really have to. All of these things disproportionately affect other groups other than myself. And that means that I'm often surprised when I read, and it tends to be that I'll read things and learn about things. I'm like, oh, in hindsight, that's obvious, but it really wasn't obvious to me. So that's one of the things that I'm going to try to do in this collection of things that I'm about to talk about is things that jumped out to me as, oh, I really should have been thinking about that. So let's start with the sort of more obvious ones. Power consumption. This is sort of a graph of the size of neural networks since the beginnings, 1960s. And this growth of the size over this time, that's basically at about the same rate as Moore's law. Networks have been getting bigger, Somewhere around 2010, 2012, all of a sudden things start shooting up and networks are just growing and growing and growing, and no one expects that to stop. What's that mean for power consumption? So training one network is still not too bad. So this is sort of a graph of just sort of carbon consumption of a bunch of sort of typical things that people are used to. Training one network is not too bad, but the fact is that in practice, whenever people are training a network, we also do hyperparameter optimization and we try lots of different things. And we're starting to get huge numbers in terms of the cost of training some of these networks. So this is pretty clear. This is one of the things that at least Neuromorphics, hey, look, this is exactly what we're supposed to be dealing with. This is exactly dropping the power consumption of this stuff that would be really useful. There's a couple interesting suggestions I particularly like. They specifically call out, hey, computationally efficient hardware algorithms, that would be great. Also, reporting the training time and how, if you're going to do one of these large, giant hyperparameter optimizations, report what you found. Like, don't just give me the best fit, give me the rest of the data, because then other authors can then know, do I have to do this broad experimentation or not? There's also been a bunch of calls out of that sort of community that, hey, because of these costs, giving remote access to your resources is an important thing. So that's, again, something I think this community can be focusing on. However, it's also really important to realize that there's a standard paradox in making things more energy efficient. There's the rebound effect. If you make things more energy efficient, people just do more of it. And there's lots of examples in the literature. It doesn't happen all the time, but there are examples in literature where you make cars more efficient, people travel more, the total power consumption just goes up. So it's not necessarily clear that having it's certainly having more energy efficient neuromorphics is going to change what people do. I'm not sure we should be thinking about it as something that reduces the power consumption of overall machine learning. But hand in hand with these big giant networks is also these large data sets. And the large data sets, it's been quite surprising. The fact that when you get these large data sets, I was not really aware of just how little we know what's in these data sets that we're training our systems on. This paper up here was published in 2020 about a data set called the Tiny Image data set that was been around since 2006. It's one of these data sets of here's a bunch of images and labels for those images. And they pointed out in 2020 that, hey, one of those were, here's the category, here's a bunch of images. Yeah, one of those categories is the N word. And there's a bunch of other equally problematic categories. And it took until 2020 for people to notice this, or for people to notice this and care about it. And, just so the fact that that can even happen was really surprising to me. The data set has been removed, and this is the message on the website. If you try to download it right now, they're like, yeah, no, that was bad. But this is still something that's happening with these large data sets. GPT-2 and GPT-3, these sort of large language models that have been trained recently, it's not really clear what they were trained on. GPT-2 was trained on Reddit links with 3 or more karma. That was the sort of source of data. GPT-3 was trained on using another neural network that would find web pages that are similar to the sorts of things that GPT-2 was trained on, whatever the heck that means. And then they were filtered somehow. And again, it's not clear. There's other data sets that have done things like, oh, okay, we're going to take these large data sets and then just discard pages with naughty words, which of course has interesting side effects like all LGBT content gets removed. So there's a bunch of interesting puzzles in there that people can, that when you're putting together data sets, that we need to be a little bit more aware of to hopefully, to see those sorts of things. Particular ImageNet, which is something that is extremely commonly used. There's been a bunch of interesting analyses of, well, what is the representation of people in that data set? And in particular, the sort of, here's a bunch of pictures of particular categories, and they are much more skewed than the actual population distributions. So there's been a bunch of approaches to try to rebalance those data sets to at least bring the skew back to at least what the population level is, or even eliminate it altogether. And that sort of highlights, so one of the things that neural networks tend to do if you train it, so it's not just okay, you want to get a balanced training data. You also want to make sure that your neural networks are not accentuating that biases in that data set. So this is a fairly popular example that's been out there of, oh, hey, look, here's a language, here's a translation system. On the left is the original Hungarian, which doesn't have gendered pronoun markers. When you translate that from Hungarian to English, the network's going to pick up on underlying patterns in the training data, but it's going to accentuate them. It's always going, it's going to make these sorts of mappings of okay, we'll assume that women are the people that cook and men are the people that teach. We're going to make those things sort of 100%, even though in the data set it certainly was not 100%. How can we actually go about sort of really pushing those sorts of things a little bit more? To summarize those quick little bits that I was just saying there, one interesting thing in the neuromorphic community is we tend not to be using giant data sets. We tend to be building, either making our own data sets or using sort of more specialized data sets for particular tasks. I think we as a neuromorphic community also have this opportunity that, hey, biology often learns from smaller data sets. Biology often does online learning. So I think we have some potential for at least making sure that we are understanding what data sets that might be small enough that we can actually understand what we're training their systems on. And if we are making our own data sets, the fact that we can learn these from these lessons of, hey, look for these sorts of problems. And I think there's also some interesting hints about how we might modify algorithms to also take this, the fact that even if our data sets are reasonably biased or are reasonably unbiased, we still want to be looking at it at the algorithm level. To highlight that a little bit more, I'm going to focus on an example from this book here, The Ethical Algorithm. which I think was the first time for me that it really drove home to me. I had finally had an understanding of why it is that these networks are, well, what's going on in these networks that is leading to these biases happening. So here's some data that we might want to get a network to classify. I've got two inputs. It's, I don't know, we're going to be, hey, this is maybe your grade point average and your SAT scores, and maybe what the classifier is doing is predicting, will this person will this person pass a I don't know, a university program or graduate from a university program. And here's our training data. And you could imagine that a classifier could do a reasonably good job of, putting a line across there and saying, oh, okay, or even, it doesn't even have to be a straight line. It could do a reasonable classifying job of saying, making this categorization of, will this person, do I predict that this person will succeed in the college program? But let's say I've got this population, I've got this group of data, but let's say I've also got a minority population where the data looks like this, okay? Where I've got, all right, so again, it's nice and, actually this is nice and clean data. It's really easy to classify this data. But two things to note about this data, it's, there's a smaller number of data points, fine, it's a minority. And due to whatever background reason, the information, okay, the scores are shifted down a little bit. Okay. Now, what happens if I go ahead and train a classifier on this? Here's the full data set with both of the groups put together. And if I go ahead and train any system on this, it's going to do something like draw a line right there. And this leads to one possible definition of fairness, one possible definition of what it is that we might want out of our algorithms. What is it that's intuitively wrong about this line there? Because what this line here is doing is it's just saying, okay, look, I'm only ever going to predict that green people will ever pass college and orange people are just never going to pass college. That's what this classifier is now saying. And so one possible definition of fairness is something like, well, I would like it if my networks would have a false negative rate that is similar across groups. Okay. There are lots of other definitions of fairness. One of the key points of this book is actually that there are many competing definitions of fairness, and they can be shown to be mutually incompatible. But in any case, that is one thing that we could describe as something that we would like out of our algorithms. And this is also an interesting case for me where, well, here's a case where the normal solution of, oh, just don't feed in population information into your network. Yeah, that's not going to solve this problem at all. In fact, if I feed in the population information into my network and have three inputs, GPA, SAT score, and what population you're in, then it might be possible for this classifier to do a better job. Unfortunately, another key point of this book is pointing out that, hey, that's not guaranteed. If I had just added in a third input, which is what population they're in, and trained up my classifier, the system might just use those extra degrees of freedom to just do a better job of classifying the green spots. In general, one of the key points in this book is if you're training a neural network and you have some loss function, yeah, it's just going to focus on that loss function. It's not going to do other things like, oh, I hope it will be equitable. I hope it will be fair. And instead, what they're highly recommending is just go ahead and just include this fairness right in your loss function. And you can get this interesting trade-off of, oh, for a little bit of loss in accuracy, you can get increases in fairness or decreases in unfairness. It's a huge topic. I found this was the best reference and I sort of the most detailed stuff about really getting into the details of let's try to make the algorithms and take this stuff into account in the algorithm itself, with a key highlight of that anytime we try to make these things more fair, we are by definition going to be decreasing their accuracy in an unfair sense. So anyway, so that is at least helps give me a little bit of an intuition about what's going on, why it is that we get all of these all these results out there, like, oh, hey, look, here's a bunch of different recognition systems that just fail miserably on different classes of people. So that's sort of, again, I think these are examples that are hopefully familiar to a lot of people, that a lot of facial recognition systems just don't work or have very high error rates when you have people with darker skin. And there's all sorts of interesting approaches of how to measure that, how to adapt your algorithms to deal with that. There's some really cool things about actually also including your loss function, making it not possible for the system to predict different traits. So some really neat work in there. Also some really good work that's pointing out that you can't just look at these populations individually. Okay, I'm almost done. My hope is that fairness one at least was relatively uncontroversial. That this is something that, okay, this seems work. I'm going to end with possibly a more controversial one. And this is just the, there's this question of who benefits from your research. There is the extreme question of should some research even be done? So questions like, do we, given how states tend to use surveillance and how it tends to use them against minorities, does it make sense to even be working on improving facial recognition systems? Does it make sense to be working on drones with guns on them that can make the decision on the drone itself whether to shoot them or not? Those are interesting questions. They're really hard choices. If your funding or your students' funding depends on those tasks, it's not as cut and dry as I'm attempting to make it to be. But I think even, and I certainly think that given the fact that the neuromorphic engineering community is reasonably small, and we have such a specialized skill set, I definitely think there's, I don't have much sympathy to people in this community falling back on the, well, if I don't do this particular research, someone else will. It's a small enough field and it's specialized enough skills that, no, if you choose not to do something, it might be that no one else will do it, or at least no one else will do it in the near future. So I think that's worth considering. A less extreme version of that, if you do have the ability to choose a little bit about your research, this question of who benefits from your research, take a look if there's different audiences that you can be working on the same type of work but different things. Here's some data set from natural language processing pointing out that basically no one, so there's 1 billion people in the world whose first language is not studied at all by anyone in the NLP world. And then even more commonly, so the vast majority of the research happens on these particular a set of 7 languages. There are other places that one can target, and so there's some interesting questions like, oh, well, especially given the energy consumption stuff that was talked about at the beginning, does it make sense to, and this is an actual example, $150,000 in energy consumption in order to improve English to German translation by 0.3%. That's an interesting choice. And I'm definitely not saying that that's a wrong choice. There's all sorts of other, but I do think it is worth at least considering if there's possibilities that one can study other groups. And even things like gesture recognition, ASL, and less common sign languages could be interesting targets. Anyway, things to be thought about there. Who is benefiting from the work? Okay, overall conclusions from that bizarre whirlwind of things. Examine your data sets. I think in this community, smaller data sets may be easier to understand and curate. If we're going with biological inspiration, biology somehow uses small, there's still pretty big data sets, but it still uses smaller data sets somehow. So I really like work in that direction. If you are doing algorithm research, and many of us in this community are coming up with algorithms, see if there's ways to include fairness in these algorithms, and certainly don't just assume that it'll come from having good data sets. If you can, if you're in the situation, look to expand who benefits your research. And if you're looking for a particular set of sources for reading into these areas more, I think these are the two that I would really focus on. The ethical algorithm for really pushing the, how do you look at algorithmic details in this manner? And then also this paper, the stochastic parrots paper, this is the paper the Timnit Kabru was fired from Google for. It's just a big collection of, here's a bunch of stuff of various different existing published things. It's just a collection of results, and it's a nice condensed read for that sort of thing. All right, I hope that was somewhat controversial. I assume there will be some discussion now and hopefully future discussion in the Slack channels, and thank you.
Well, thank you.
Since it is a discussion, yeah. So can I raise something, Andreas?
Yes, go ahead.
Yeah. So this whole problem of dealing with imbalanced data sets, basically you're dealing with a problem of imbalanced data sets, right?
That's one place.
In a lot of these situations, exactly the same problem that we face when we're trying to train networks on control data. 99% of the data is very boring and it is completely useless and redundant. And the 1% of the data is when you're about to crash is very valuable, but we don't know how to get our networks. So even with methods like focal loss and stuff, we're not able to train our networks to deal with these exceptional situations and also deal with the common situations reliably. It's a really big problem.
It is a problem. And I think that problem also extends to the field of medical devices and medical diagnosis, where most of the data are collected is biased. And so the solution, one solution to that, but I don't know how you deal that in control, because you're really trying to learn the model, is to have a model that generates data. One could have a model of pathology, and in a medical device that actually will generate a supercomputer model that will generate pathological data given large, small size people with different anatomy. And there is a big project in Europe, in Switzerland, of really, for example, in this case, building anatomies, human anatomies, to really take into account the physiology and of the human physiology and the sex and all that. But I don't know how that translates to control, and I don't know how to do that in language, I think. But I think this is the kind of questions that, from very practical to very general philosophical questions that our community, we should be having a discussion continuously. It's not something that we discuss now and it's done. I assume I want to have this as kind of a background activity for our workshop, to really be looking at things that, and changing the topic back to the SPI interface. We shouldn't be writing papers with diagrams and offending terminology, period. We should start using or code. You write in your code often, ZFS, the file system has master-slave terminology built in the code. This is the kind of, sorry, I
agree. I'm certainly really curious about how this. I'm looking forward to the ongoing discussions throughout the workshop. I would be really, Toby, getting back to what you were saying there, I'd be curious whether or not some of the fairness, like the embedding things into the loss function about fairness.
Yeah, but why don't you just explain a bit more about what you mean? Why don't you just go back to that graph and explain what you mean about graphing?
Maybe Toby, maybe this is something we can do in a future discussion group.
No, not that. I was talking about your loss curve, right?
Oh yeah. Okay. Yeah.
Oh yeah.
Okay. Right. That.
I wanted something concrete, right?
Yeah. So this is if you're included in your loss function, you need to include some sort of scaling factor. But how important is it in your loss function? Right. And so as you adjust the importance of that gives you different points on this curve. And this curve is trading off accuracy versus unfairness.
Is that a global parameter, Terry?
How do you measure this unfairness? What's that measure?
And the unfairness is exactly, so you take a look across a bunch of groups, you find the rate of false negatives after you've trained it, all right? And then what's that distribution look like? Is that a, you know, how uniform is that distribution?
Yeah, it's like a ROI curve, yes. Yeah. Or the better version of the ROI curve that, right, is balanced. You know, ROI curves tend to, I forget about that. ROI curves per se are not really good at dealing with unbalanced data. This is the same problem.
Yeah, this is just measuring the effect of how ununiform those distributions
right,
are.
exactly.
The hope is that it ends up something like this, where it ends up being a fairly natural point here. They do also point out that's not guaranteed either. Like this curve could, you know, look this way. Which, great, all right, then you just can't have a fair system of doing it.
What do you mean? You want to get a point like with this inflection where you can pick that point right there at 0.123 or something?
Yeah. Well, I mean, this is at least indicating that for a small decrease in accuracy, I can get a big increase in fairness. Right? And that's not necessarily guaranteed.
That's the cost of fairness. How costly is fairness in accuracy? Yes. Which is another parameter that someone would pick.
Yep. And then if I'm working in a domain where no, fairness is really important, I'm working on a model that's, I don't know, deciding who gets bank loans. All right, then maybe I'll pick this point out here. I'm not as accurate, but I'm way the heck more fair.
So this is quite interesting. So this is posed in the context of a classifier where you have a classification result, which is a binary result, right?
Right.
But what if you're solving a regression problem?
Yep.
You know, where you have to predict.
Yeah, I believe they were talking about those categories in there in these models as in a regression problem. I don't know if there's examples,
but
I'll check.
Terry, maybe we can invite Michael Kearns to just give I mean, I know it's difficult. This is a problem with discussion groups. You know, you find all of these things and then someone either has to go and do a summaries because I don't think we can get him to probably come and give us a half an hour to Laura.
I would love to do a little reading group anyway on some of the sections.
Yeah, we can do a reading group. Exactly. This is really what the discussion group is about. And you can invite him next year.
In the interest of adding some entropy into the discussion group, I have a challenge for our community. So this is obviously a hugely important topic, and it's one that is increasingly efforts to address it in machine learning across, you know, all of many aspects of the traditional machine learning field. And one of the questions that we have for ourselves here is, you know, what can the neuromorphic community do in and of itself that's, you know, distinct and impactful beyond a lot of the existing efforts. And one area where when I look at a lot of today's fairness work, it's understandable, but it's not surprising, but it is oftentimes coming from a pretty North American centric context, you know, in terms of what is important ethical work, and, you know, what are the societal factors that are that we're trying to, you know, prevent harm in certain contexts. And so one thing that we should consider is how can we use the international community that we have here gathered together at the Telluride workshop to think through what are some of the implications for the entire world? How do we make technology work for developing countries? How do we make technology work for people who have significantly less resources to engage with technology right now? So I think there's something to chase there within the neuromorphic community in particular, because we have such a international community here. I would be really interested in perspectives from people who land outside of the North American you know, context, and it'd be really cool if we could do something novel in that area.
Well, that's great. That's a great suggestion, Guido.
Yep. Anyone who is at all interested in that, please join the discussion channel, and I'd be very curious.
And I'd also like to point out, there's actually a interesting article called Machine Behavior, which came out from a number of machine learning researchers. And and the gist of this is that, we are training through machine learning algorithms which we don't understand, which leads to these problems of unfairness and so on. So it's a black box. And so the same tools that we use in order to understand how our brain works from behavioral data can also be used to understand these. And so I think the opportunity here is to expand also this neuromorphic engineering machine learning community to the fields of cognitive sciences and psychology, because those same tools, the statistical tools used to understand the behavior in humans, can actually also be used to understand fairness. So I think that's a really nice paper, and I'll put it on the channel.
Yeah, please do. By the way, one of the speakers we had we're hoping to get a speaker from Pagnell who is cognitive neuroscience, but he just couldn't do it. It was just too much. But hopefully we'll have him next year, and others to really address this question, Emery, that you're pointing out. Yeah, relating to neuroscience and neurobiology of human behavior, I think that's really also important.
And the fact that cognitive psychology has developed a lot of tools for at least attempting to address a lot of these things.
Yes.
Maybe somewhat, or at least study it.
Yeah, I really like that. That's kind of almost the social behavioral cultural version of could a neuroscientist understand a microprocessor?
Yeah, so that's really exactly that. Yes.
Which is a fascinating paper in and of itself.
Yep.
Pull that.
Are there any comments from others that have experience in this area or suggestions? I'd love to hear from other people too, besides us here.
So,
Feel free to speak up.
this is Soo-Siang Lim from NSF. Hello?
Yes.
Yes, hi. I think it would be important, Andreas, thank you for initiating this discussion to Telluride. It'll be important to kind of go beyond this community, because these are questions that the larger communities beyond Telluride are grappling with, and then to scope out perhaps the issues that are most particular to some of the projects that you're currently engaging in and training students. And a plan to say, where would you get the necessary expertise of people to talk about these, specifically for neuromorphic engineering and also to the larger community? How would you implement what you have learned from these groups, recommendations or considerations? And importantly, we're bringing these issues up because you're developing a lot of technologies, and it will be important to integrate these considerations early in the design of the technologies, rather than after the fact and say, well, actually, this may not be a good thing to do because it has certain biases that were incorporated into it. So this is why it's so important, and Telluride is a particularly good place to start because the students are there, and I don't think anybody has answers to it, but to really have a mechanism to hear all perspectives, understand the scope of what you can do as a community, and train the people to ask these questions even as they generate new technology.
Yeah, absolutely. I mean, I'm really excited actually that we were, I mean, we get to work on this. And I think, as you pointed out, we can be impactful. We have the students, and we can be broad. And also we'll probably end up writing a report at some point. It will be a kind of a living document, a working document about our findings. And we want to have people from cognitive sciences. I mean, we had some speakers planned, but they couldn't make it. And so we really want to look at the broader community, get some science and really address that. And I think it would be one of our objectives to really be trying to accomplish something like this, as you suggest.
And I really like the Go ahead.
So one thing perhaps as a deliverable from this first initial discussions is a plan, right?
Yes.
For discussions and to get the buy-in of the community on what things they would prioritize and how broad, what are the issues. And Terry, you brought up the whole thing about leveraging the international communities too, because they may have very different takes and constraints on some of these issues. And I think it'd be good to have those kinds of understanding too.
We'll definitely have a draft report by the end of the workshop. This is really a plan, at least, of how we will move on.
And experts that you will be recruiting in future meetings in a systematic way.
Yes. And also incorporate, we like to connect to the other networks groups, because they may have, and we plan to do that. We actually, we've talked about that, and this is just the beginning, but.
Right, you want to reach out to the Fairhall AccelNet group, right?
Yes.
They are also doing the same things. And I don't know if Grace is still on. Certainly.
I'm still on.
Hi, Grace.
Hi.
By the way, Grace, I'm the culprit of trying to make you attend this workshop. I put your name on an email list and you probably got a connection. I'm glad that you're attending.
Oh, thank you for that.
So Grace, it seems to me that, the kinds of works for the announcements for future from engineering, whether it's BRAID or the existing communities, we all share the same issues that we're facing now that has become, that is really coming to the forefront of NSF priorities as in terms of our AI neuroscience intersections, right? So.
Absolutely, and there's a lot of energy for us to connect with the folks that run the ethical and responsible research solicitations and SBE. And there's some resources that if folks need, I'm happy to put in the Slack channel. And I know in neuroscience, anyways, the Copley Foundation and at the recent BRAIN Initiative meeting, there was a whole section put away dedicated to ethics and responsible research. And I wonder if some of those experts might be people that you could perhaps invite to in the future.
Yes.
Right. Like Society for Neuroscience. And SBU also has another program on, I think it's law and technology and society. So there are also experts who are funded by NSF who are looking at some of these issues. So you as you develop the plan, let us know if there are particular areas that you're looking for. Now I could always check with my NSF colleagues to get some names.
That's great. Thank you.
Yeah, thanks. Good. Is that it now? I guess that's enough for one day, right?
Yes, I think it's enough.
It's enough for one long Zoom with no breaks. So we intended to have breaks, but of course we didn't actually have any breaks. So next time we're going to have breaks. Okay. Okay. So from now on we have breaks. That's the rule. Just like in Telluride we have the sports break. At least here we have the get up and walk around break.
Yes.
Okay, so now I think the last event is unofficial event, but Sim, in the tradition of Telluride, will attempt to start a poker game.
That's right. Okay, so the game's running now. The link is in the general channel of Slack.
Some people have to have dinner or whatever. Yeah.
If you fancy playing poker, the game is running from now for at least the next 45 minutes. It's like
by the way, this game is with fake money. There's no real money.
Toy money.
So I should really, for honor. So we don't get our sponsors in trouble.
Actually, I've been doing this a lot with my family. The best way to start a random timer, and then when the timer goes off, whoever has the most money left, this virtual money is the winner, second place, third place. That's the best way to do it, Sim. So fire up the random timer.
Okay. So with this topic, can we wrap up the official group? Yes.
Yeah, I guess that's it. Thank you very much. See you all tomorrow then.
Yes.
And keep the questions coming on the questions channel of the Slack, and the speakers will address them and we can get something lively discussion going.
Yes, and
It was
thank you,
very nice.
Grace, Soo-Siang, and Claire for really attending. Yeah.
Thank you for inviting us. Is the topic 2 going to be discussed at some point?
Topic 2.
How do brain
Yes.
machines that learn to configure
Yes,
themselves?
yes, yeah, that would be another. I mean, we want to get going on the social, and then we also want to address that too. Just join the Slack discussion, and we'll get on that as well.
Congratulations on a really good meeting.
Yeah, thank you. Thank you for
Thank
your
you.
comment.
Claire, thank you.
Thank you so much.